Hello class, this is CSE-5250, sections 2 and 60, week 6, spring 2026. So by this time, you should be already finished with your first round of benchmarking. So now let's begin with looking at chapter 5, that is OpenMP. So, OpenMP is yet another API that we can use to write parallel programs, specifically shared memory parallel programs. OpenMP allows the compiler and runtime system to determine the behavior of threads, and it makes it easier to work with. It's easier to work with compared to, say, pthreads. OpenMP was developed by programmers who thought that writing large-scale, high-performance programs using APIs was too difficult. So what OpenMP does is it abstracts a lot of the work needed to write a parallel program so that the overall effect is that it's just way easier to write a parallel program. We're only going to go as far as writing the Hello World program for this video. Next week we'll talk about more about what we're going to do next. It's not a pi estimating program, it's something else. So to get started, we can write a simple Hello World program such as this. So, include standard I/O, include standard lib.h, and here, the omp.h, that is the include. This is what you include to work with OpenMP. So it's gonna mirror what we have for the pthreads program, except notice that we don't have any code related to allocating thread handles and all that. Rather, the only parallel additions that we have to make here is just a simple directive that is on line 11. Pragma OMP parallel numthreads thread count, where numthreads, that it looks like a function but it really isn't. In this case, it's part of the directive. Numthreads, and then you pass in a number that specifies how many threads the program is going to work with. So this is a compiler directive, and all the work needed to fork and join these necessary threads is done at the compiler level instead. So if we just remove line 11, then all you have left is a simple single-threaded Hello World program. Just by slapping in that pragma directive, you have turned that program into a parallel program. That's how easy it is. The command to compile this program is as follows: gcc-g-wall-f openmp-o, the name of your executable, and the name of your source code file. Oh, by the way, you can use C++ with this. If you do, swap out GCC with the G++. So, I'll demo writing this program as well, but when you do run this program, it's going to be the same thing as before, /program name, and like the pthreads Hello World program, it is set up such that we must pass in a quantity of threads as one of the command line arguments. In this case, this is 4 threads, so you'll have something that looks like Hello World from thread 0 of 4, 1 of 4, 2 of 4, and 3 of 4. And like with pthreads, the order in which these threads run is going to be random, and that randomness is determined by the CPU scheduler of your operating system. It's just gotta be random. That's just the nature of parallel programming. Oh, by the way, if you are working on if you are using a Windows system, or more specifically, if you are using Visual Studio on Windows, I have included steps for how to set up a Visual Studio project so that it works with OpenMP. Here you have a lot more freedom with what system you want to work with. For consistency's sake, I'm just gonna continue to use my Ubuntu virtual machine for this, but do note that you have the option to now use a Windows machine. If you have Visual Studio, to turn on OpenMP support is simply just, once you have your project made, go to the Projects tab, go to Properties. Because OpenMP support is disabled by default, you should get this pop-up window, go to Properties, and then C/C++ language, find the option for OpenMP support, and set that to yes. If you copy the code exactly as I had from a few slides ago, and you try to run it using the Visual Studio's debugger, you'll get a debug assertion failed error that might look like this. This is the equivalent of getting a segmentation fault, which only happens if you forget to pass in a quantity of threads as a command line argument. There is a way to work around this by just hard coding the thread count, and you can do that. It's just you're just gonna have to re-code the program every time you want to change the thread count. So if you want, So if you want to run your program on Visual Studio and using Windows, using the exact code shown previously, first press Ctrl-Shift-B to build your program, and then in the Solution Explorer panel, which should be by default on the right-hand side of your Visual Studio interface, right-click the solution, that is solution, and then in single quotes, the name of your project. Right-click, you'll get a menu that looks like this. Select Open Folder in File Explorer, and you should find yourself, well, in the folder itself for your project. So, somewhere in here is a debug folder, and somewhere in that debug folder should be an executable. This is the executable you are to run. So once you are at that location where the executable is, type in PowerShell into the address bar, and use the same command as you did before, as though you were working with a Linux system. So that is / executable name, and then the number of threads you wish to work with. Once again, I'm going to demo this to you as well. So, let's look at that code really quick. So, of course, we need to include omp.h. But it's not just OpenMP stuff that is within omp.h. We also have several directives, all prefaced with #pragma. So, pragma omp parallel is one of many such directives. And omp.h, we just include that like we would any other library. So, line 7 is going to mirror, as I said, the code for the pthreads programs that we've been writing. Basically, it's set up so that when you run this program, it'll accept command line arguments that we can just pass in and then parse as arguments for the program that you work with. Line 9 is that strtool function again. That's just gonna convert one of our command line arguments into a thread count. So the first argument is the argument itself. The second argument, just set that to null. And the third argument, that just specifies that we're just going to pass in 10 because it's base 10. So line 11, that is that parallel. So pragma omp, any code following pragma omp is a parallel section. And if you have multiple lines that you want to be a part of a parallel section, you gotta enclose that all in curly brackets. So this hello function is being called as part of a parallel section specified by this pragma omp directive here. Well, technically it's pragma OMP parallel and then num threads thread count. That means that program is going to fork. Each thread is going to call hello, and then once all those threads are done running the hello function, they're all going to join back. So it's the fork and join model, but notice that we have not written any code at all needed for... There is no explicit fork, and there is no explicit join. It's all implicit, just by having this directive here. So, once again, it's the fork and join model all over again. There is going to be some thread that is going to be the master or main thread. That is the thread that is assumed to be... That is the thread that is going to be the first thread to be created. That is thread 0. That thread encounters that parallel directive, and it creates a team of threads. So, basically that thread is the parent. And then all those child threads that we created, it and the main thread are going to call that function that we had there, the hello function. And then once they're all done, they are going to hit a barrier, or an implicit barrier. And then they're just all going to wait for everyone else to finish, and then they're going to join back in. It's the fork and join model once again. Okay, so that example had no means of error checking, so it's a good idea to have some means of error checking. So, with the possible issues with this particular program, they're going to be the same issues as before with the pthreads program. You must pass in a command line argument for the number of threads to run. You can hard code it if you want to, or if you want to go above and beyond, you can add some error checking and then just go with the default value instead. Also, if your system does not support OpenMP, all the OpenMP directives are ignored. However, you might still have problems because if you include omp.h, that if you have that and OpenMP is not supported on your system, it's just going to throw a compiler error. Like, basically, this thing cannot be found. So, those are some possible issues that you might have with the program, and what happens if you don't have OpenMP installed on your system. So next week, I would like for us to look into writing our first parallel program using OpenMP. This is going to be an implementation of what is known in calculus as the trapezoid rule. It is a means of estimating the area under a curve by cutting up the area under a curve into a sequence of trapezoids and then adding up each trapezoid's individual area. And the idea is you get all these trapezoids are of the same width. The smaller and smaller you make that width, the more and more trapezoids you have, until you have infinity trapezoids whose width is basically 0. Or rather, more specifically, the number of trapezoids approaches infinity, and the width of each trapezoid approaches 0. So that is something to look forward to next week. So, right now, I am going to open up my virtual machine so we can then try out OpenMP for ourselves. Okay, so let me just create a new file like this. There we go. Open up the document, and all of this is all our code from all our pthread stuff. I'm just gonna close all that, and now I'm gonna put my slides to my side monitor so we can then look into writing this program. So there are 3 include directives that we have to add. Let me just add a comment up here. Okay, so there are 3 include directives here. Standard io.h, standard library.h, and omp.h. We're going to write a function prototype up here. So void hello, and then void, there we go. Here's our main function. So int main, and then parentheses, int argc, comma, character, star, argv, square brackets. Let's get the thread count from the command line by writing in int thread count equals strtol, and then in parentheses argv 1, comma, null, comma, 10. And here's a parallel section. So pound sign, pragma, omp, parallel, num, threads, thread, count. Now, our parallel section only consists of one line of code. If your parallel section consists of multiple lines of code, it must all be enclosed in curly brackets. I'm just going to enclose them in curly brackets just for consistency's sake. So I'll just write hello, and that's our function call. Okay, and then return 0, and that's it. Well, apart from the fact that we have to write the function implementation, so apart from the fact that we have to write the hello world function, that's it. That's all the code you need to write. There are no function calls needed for forking. There are no function calls needed for joining. There are no function calls needed for allocating thread handles or anything like that. All that stuff is just handled by the compiler. But you do get a few other functions that are probably going to be worth working with, such as how do you know each thread's rank? So back with the pthreads hello world program, we had to pass in a rank that basically identifies which thread is which. We don't have to do that here with OpenMP. Rather, there is a OpenMP special function that gets you the number of threads, and yet another one that gets us that thread's rank, or thread number. So, to get the rank of a thread, all you gotta do is use this function. OMP get thread num. That's it. The other function just gets us the thread count. So, with the pthreads hello world program and all the other programs that we wrote using pthreads, we used a global variable that would store the number of threads that the program is working with. We don't have to do that here either. As I said, there is a function that lets us get the thread count as well. So, int thread count equals omp get num threads. Now, these two functions have near identical names. Did you know that in California there is a Claremont, and then next to that there is a Montclair? Yeah, that's what I mean by near identical names. So one is for the thread number, and the other one is for the number of threads. Do your best to not mix them up. Finally, let's write in a printf statement. Printf, and then I'll just write in once again, with pthreads, we have to pass in the rank into that function. We don't have to do that here. With pthreads, we had to store the thread count as a global variable. We don't have to do that here either. Those are both handled by the functions threadnum and numthreads. Okay, so that's our whole program. Let's compile this thing. So let me just make sure we have that file there, and I'm gonna type in the command gcc-g-wall-f openmp-o. The program is called openmp hello. And then the source code file is, there we go, /openmp hello. And there's a segmentation fault because I did not add as a command line argument the number of threads to run with. Let's do that with 6 threads, and there we go. Hello world from threads 3, 1, 2, 5, 4, and 0 in that order. When you try this, it's, as I said, it's going to be random. We can do this with an arbitrary number of threads, and at the programming level, we do not have to worry about this. That is done at the compiler level instead. So let's do like, let's do 37 threads, and there we go. That's all 37 threads. Oh, by the way, one other thing I can do is this. I'm going to comment out that assignment operation for thread count, and then I'm just going to remove the numthreads thread count from that directive, and I'm going to recompile the program again. If I do that, it does not matter what I also pass in as well. In fact, I'm going to remove the 37 from there. And look, if I just have pragma OMP parallel and I do not specify a thread count, it's going to default to however many threads your system can comfortably handle at once. So this is a 6-core system. Here, it's gonna run this program with 6 threads by default. Okay, so that is your Hello World program. Let's try this again on a Windows machine. So here I am in Visual Studio. I am going to create a new project, and I am just gonna select empty project. Next, I am gonna save this in a suitable location, and I'm gonna call this SPR 2026 OMP hello. Enter, and let's wait for this thing. Your version of Visual Studio is no longer supported or serviced. It's basically asking me to upgrade to Visual Studio 2026. This is 2019. So I have been using this program for a very long time, and now there's a new version. I'm just going to proceed anyway, so right now there's nothing in here because it's an empty project. I am going to move my face cam to the side so you can see the Solution Explorer panel here. Right click, Properties, and there's nothing because there's nothing in here. No, I'm instead going to click Add, New Item. I'm going to type in main.cpp. And there is our source code file. I'm going to zoom in a lot, and then I'm going to write the same exact program again. so that's most of the program there. Finally, alright, so that's our whole program. So we can just debug this now. Not really. I'm just gonna abort that, and here's where... Okay, so if you want to just run this program without using PowerShell, the way to do that is to just bypass this step entirely. So comment out int thread count and all that, and then remove this part. Or rather, just hard code the thread count as... Hold on. Okay, so if you want to run this program without having to pass in a thread count as a command line argument, all you gotta do is either comment out this, either remove this and this, or just hard code the thread count as, let's do 10 threads for now. And now let's run this using the debugger. And that ran so fast that it closed immediately. So I'm gonna press Control and F5, and hey, it's supposed to be running with 10 threads, not 1. And that's because we forgot an extra step. Go to Debug, go to Project Properties, you'll get this window. Go to C/C++ and look for language. Should be down here, right in the middle of these options. Find the option for OpenMP support. Select yes, click apply, click OK. Let's try that again. And this is the debugger. Look in this debugger. No, press Control F5. There we go. Now it's running with all 10 threads in no particular order at all. I say that when all the threads are coincidentally in order except for 2 of them. Let's do it again. And now they're in order this time. Okay, so now we have it working, but what if we want to run it the same way as it was with the command line arguments and all? Well, for that we need to right-click the solution in the Solution Explorer and click Build Solution. And you can see in the bottom left of the screen, we see Build Succeeded in the bar down here. Now, I need to right-click the solution again and open a folder in File Explorer. You're going to see this, and you're going to see a debug window. You're going to see a debug folder in this window. Open that, and you should see an executable in here. Now, it might be a little bit different if you are doing this as a 64-bit program. In fact, I'm going to change it to a 64-bit config, and instead, I'm going to rebuild it now. So the 64-bit version is going to be in an x64 folder, in my case. And in that is a debug folder, and in that is your 64-bit executable. Let's go back to the 32-bit version, which is going to be in the debug folder up here. And there's our executable. So how to run this, we type in PowerShell into the address bar, and we can just use PowerShell like we would the Linux terminal. So that is going to be not slash, I'm going to do ls just to prove my point, and there is our executable in there. The command is dot slash SPR2026 OMP hello.exe, and let's pass in, let's do 5 threads. There we go. All 5 threads running in no particular order. It works. Nice. Now, this is a C++ program, so everything that you're familiar with C++, it's available to you. With one specific caveat if you are using IOStream. And I'm going to demo that right now. Okay, so what happens if we use IOStream and cout instead of printf? You're gonna get something that is reminiscent of a race condition. This demo that, I am going to build it, and for the sake of time, I am just gonna hard code the thread count to 16. And then I'll just run it using the debugger up here. So I'll just switch it back to x86 just for consistency's sake. Run in the debugger. It ran too quickly, so it's got to be Control F5. Yeah, see that? It is. So if you think of each part here between the chevrons as something that's being written to the console, that is the kind of race conditions that we're having here. So for that reason, I advise not using IOStream unless what you're printing out is you're able to get it concatenated into one big string, and then and then cout that. Otherwise, use printf instead. That way we don't have this mess happening. I'm gonna demo it once more with 16 threads. Oh, and by the way, my virtual machine only has 6 CPU cores available. My main machine has 8 cores, 16 threads. So by default, if I ran this program and I did not include this num threads here, it's gonna default to 16 threads. So to demo that, there we go, 16 threads. I'm just gonna force this to be 24 threads for the sake of demo, and then I'm gonna type in num threads thread count, and then I'm gonna run it again. Compiler errors. I think I know what happened. I misspelled it. There we go. There we go. I forced it to run with 24 threads, even though this is an 8-core, 16-thread machine. So it doesn't matter. So really, it doesn't matter how many CPU cores your system has. The point with parallel programming is whatever we write, it should be able to work with whatever hardware is available. So if you took this program and ran it on a more powerful computer, one that has more cores and therefore more threads, basically it will in theory run faster depending on what kind of workload we have. So again, only certain types, so as we'll see with OpenMP, only certain types of Okay, so in the following sections for chapter 5, we are going to parallelize for loops. So where OpenMP shines is how we can parallelize a for loop by just adding a single directive, and that's it. But it only works for specific forms of a for loop. So there are for loops in which the result of the previous for loop iteration affects the result of the next for loop iteration. So it turns out those are the kinds of for loops that OpenMP cannot work with. If you can imagine taking a for loop and then unraveling it so that it is one block for each single for loop iteration. If you can perform that unrolled for loop iterations in any order, you can do it in parallel. That is the rule of thumb for parallelizing a for loop. So, as I said, so where OpenMP shines is the ability to parallelize a for loop with barely little effort at all. All it is just small rewrites to our program and adding one or more directives to get it to work. That's it. So that is going to be your Hello World program, and much like your previous assignment where you had, much like your previous Hello World program, you are going to write a parallel Hello World program as so. So once again, it's just going to be two things that you're going to submit: a screenshot of your program running and the source code. So what I have in here is an even simpler implementation where we just skip writing the hello function in the first place and just transplant all the code into a parallel section. So this is going to be more or less the same as the code that I have written in here. If anything, the one that I have in the instructions is a little more compact. So that's going to be your next assignment. Shouldn't take that long for you to do. So I'll have it tentatively due next week. And then from there, we're going to continue and talk about more about OpenMP. Alright, so that's going to be it. I'll have more material for next week.